Good afternoon and welcome to Lecture 2 of the Environmental Series. Today we're going to be covering the topic of minerals. And in order for you to follow along, you need to read Chapter 2 in Montgomery, Environmental Geology text, which is part of the Primus book. Now when we look at minerals today, we're going to be kind of introducing them in a general sense. I'll be looking at a variety of characteristics about minerals and why they look the way they do and behave the way they do, and even look at some of the strange properties that they have and how we've taken advantage of that. And since minerals are the building blocks to rocks, we'll then move into a segment of rocks and introduce the different kinds of rocks, some of their major characteristics, but more importantly maybe talk about some of the general strength characteristics, which is more related to geohazards. Okay? So be sure that you look at Chapter 2 for the environmental geology part from Carla Montgomery. And that should be the second chapter in your text. All right, minerals. Minerals are one of the basic building blocks that make up the rocks on the crust of the earth. And so again, we're going to be looking at a variety of characteristics of minerals. And I thought I'd start out by just showing you some different things. Now, you may or may not have seen a rock like this. That we have on the screen here. This is an agate, a Montana agate. Happens to be a slab of rock that my father actually polished as kind of a hobby he got into with lapidary work. So let's define what a mineral is first and then look at what that definition is and see what the significance of the definition is. I'll just repeat what it says. It says a mineral is a naturally occurring inorganic solid with an ordered atomic structure and a definite chemical composition. So let's just think about what this definition means. There's kind of two parts that are very important. First part is going to be what chemicals make up a particular mineral. So the chemical composition is going to be significant, the different elements that make up the periodic chart. A lot of elements you've heard of, calcium, magnesium, oxygen, and so on. They're going to combine in different fashions, and the way in which they do, of course, will control then what kind of crystalline structure is made. So let's take a look at another part of this definition. It has an ordered atomic structure. That ordered atomic structure is controlled by the chemicals that make up the particular mineral. And we'll look at a general picture of how this comes about and how this kind of basic building block of atoms becomes minerals. But I really like minerals in the sense that they're, besides being gem-like and spectacular, they're very unique. They're very different. We've got some fabulous diamonds up in this picture up here, but if you look at some of them, you can see that there's color differences. You can see that there are shape differences. Now, some of the shapes that you see here are natural. The one on the top right, these are man-made. They're faceted. They're done in a laboratory where they polish certain surfaces of that crystal to bring out the brilliance of the mineral. But in the bottom right, that particular mineral is quite unique. It's like two pyramids. It's an octahedron. And there are two four-sided pyramids up on, one on top of one another. And inside of it is another mineral. And so why the shape? Why this particular color characteristic? And of course, diamonds, are hard. So what is it about that? Here's another one of my favorite minerals, or actually two of them. The kind of sparkly gold stuff on the outside is fool's gold, or pyrite. And the other material inside is opal, kind of a semi-precious type of stone with certain kinds of brilliance, spectacular kind of gems. Your average day minerals, though, don't quite take on all that character. Now, here we have a mineral referred to as galena. It's the gray, cubic-looking minerals in this set. The reason why I bring the idea of cubic into play, because it's a shape name, it's a geometry. And why does that mineral form that way? And we're going to look at the reasons why in just a bit. Here's another kind of mineral that takes on several shapes, one of which, again, is cubic, fluorite. All right. Interesting kind of mineral, not as common as some others. Here's a very, very common mineral, halite, or table salt. Sodium chloride, something you're very familiar with. It, too, has this cubic nature. What is it? Why does it have that shape? Fool's gold, a more spectacular looking piece of fool's gold here, very sparkly. But again, here we have a unique kind of crystal form of it. It's cubic in nature. We may come back to some of its other characteristics about its chemistry later on, being an iron disulfide. But again, the shape, and if you look along some of the sides of the cubes, you can actually see another kind of character to it, kind of lineations on the sides. What is it that controls this? Well, it's the atomic elements that make it up and how they join together, and how they actually grow in place. This one's real obvious. This one is magnetic. You can see that there's metallic materials that are attached to it, like any kind of magnet. This is magnetite. What is it that makes that mineral magnetic? Okay, so different kinds of properties that we have, and here's just an assortment of other kinds of unique shapes and colors. Some pretty wild kinds of things. And in petrology classes and mineralogy classes, we discuss these in detail as to what they are. And we're going to look at some of the basic things about these minerals and the properties. So why all the different colors? Why all the different crystal forms? Why the magnetic character? Why the the kinds of densities maybe of the minerals themselves and how they might break if you hit them? In physical geology, or in any mineralogy class, the first thing we want to look at are the properties of minerals. And we have a list of these, and there's quite a long list. Here we're going to look at some of the major ones and kind of outline them. All right? So please write these down. The first one, of course, is color. We've seen some differences in colors of minerals. These are diagnostic properties that you can use to identify minerals. Crystal form. Not all crystals have the same form. Hardness. If you take a mineral and you rub it against something else, how hard will that be? Will it crush up and break, or will it scratch the surface? You know, like the test for diamonds, scratch a window to see if it will scratch the glass. That's a true thing. It will work. Cleavage is a property that's kind of difficult to understand. It has to do with how a mineral will break if you hit it or shatter it. Some minerals possess cleavage and some don't. And the kinds of ways in which minerals break and crack along these different cleavage planes will vary. And we'll look at some of the causes behind that. How heavy is that mineral? You might have two samples that are the same size, same volume, but one's much heavier, much more dense than the other. Why is that? So the list, like I said, goes on and on. There's a lot of different reasons for these different mineral properties. Well, the bottom line has to do with the atomic structure of the elements that are involved, and in particular, one part of the atom. Now, this little schematic, kind of an attempt to draw what an atom might look like, it's one of several ways we might describe and draw what atoms look like. An atom, of course, consists of a nucleus, and the nucleus contains two particles, positively charged protons, and neutral charges, no charge at all, for the neutrons. So this is where most of the mass and the density of a atom exists, in the nucleus. But more significantly, the real part that I want to look at are these electrons, these negatively charged particles that somehow go around the nucleus in some fashion, a cloud. I'm not going to go into lots of different ways with diagrams of how and where we think and predict where these electrons are. You can talk about them being in certain orbits or shells or positions around that nucleus. But the key thing, is where we're going with this, is to understand how the outermost electrons that surround the nucleus, the outermost electrons, how they behave and how they move and react as they get closer to other atoms. Something's going to happen to these electrons. They're going to change positions in different ways. Well, let's take a look at the way these do, because if I bring in a certain type of atom next to another one in a certain environment or condition, it's going to bond with that, or it may bond. So let's talk about the chemical bonding types. Let's go through a list of these bonding types. We're just going to look at three major types of bonds. Okay, the first style of bonding that you need to know about is called ionic bonding. Now, in the case of ionic bonding, this is where electrons, and the key phrase and word here you need to remember, is going to be exchanged. These electrons are exchanged, actually given up or taken on from an adjacent atom. Most minerals, there's around 3,500 known minerals. Most of those are rare. They're not the most common kinds. have and possess ionic bonding, where those electrons are exchanged with other atoms. Now, as these electrons are exchanged and these atoms join or bond together, there's a strength. There's a whole range of different kinds of strengths to those bonds. So some minerals will be more tightly and held together, a stronger bond. Some will be less strong. So they'll have different strengths, which is important, of course. That makes up rocks and how these rocks are going to fail in terms of geohazards. The second bond kind of sounds like a cooperative, a sharing experience, a co-op. It's referred to as covalent bonding, and here the electrons are shared with adjacent atoms. They're not given up, they're not gained or lost, they're simply shared at a particular site around the nucleus. And certain minerals possess covalent bonding. And the last particular bonding type we'll look at here today will be metallic bonding. Now, in the case of metals, with metallic bonding, these electrons will move freely throughout the structure, throughout the system, between all of the atoms. And when you think about electrons being electromagnetic features, okay, if you have these electromagnetic parts of an atom moving freely, metals will do what? Conduct electricity, conduct heat. So some things don't allow this, and so they're not good conductors of electricity. Things that are bonded ionically and covalent don't do that. I asked a question earlier about why is magnetite magnetic, or why are some other kinds of minerals magnetic? It has to do with the electrons. Electrons are considered electromagnetic particles. So if these particles spin as they go around the nucleus, if they're spinning in the same direction as they go around the nucleus, they're going to create a little localized magnetic field. If those electrons are spinning in opposite directions to one another as they go around the nucleus, then they cancel each other out, and there is no magnetic character to that particular mineral. So again, the electrons are very, very important in this process of creating how the atoms bond to make the minerals, what the strengths are, and other parameters. And we'll see a whole list of other goofy things that happen with electrons that are interesting physical properties of minerals. So let's take a look at how we might put several atoms together. Let's take a sodium atom and a chlorine atom. We've got a kind of a little three-dimensional diagram here that kind of shows you a particular structure as to how they would go together. Notice that the shape we're talking about here, the bonding angles, create little cubes in that case. So part of how the atoms are bonded together with neighboring atoms create a cubic structure. The bonding type is one of the reasons for that cubic nature. There's another reason why they go that way. If you ever had Legos or Tinker Toys or some other kind of things that you actually can piece together, you have a better understanding of geometry in this sense, crystal form, of how that can happen. So let's take a look at another way, another feature of what helps with this cubic nature, how these things are controlled. It has to do with the size of the atom. We call it the ionic radius or ionic radii. We can measure these with X-ray diffraction units and come up with certain sizes. We have a fancy unit name called angstroms to measure something, very tiny unit. But if you look at the picture, you'll notice the chloride ion's much bigger. It's the largest of the two, and sodium's smaller. Now, if you had to pack those together in a certain fashion, they're only going to create a certain specific kind of geometry because of those radii. You can't put them together any other way, along with the bonding character, and so you wind up with a nice cubic form. And many minerals are this fashion. So your building blocks, the atoms, along with the bonding style, are what are controlling some of the crystal forms and other physical properties of this. Now here again is halite, the more cubic form. If I were to break these pieces up, I'd simply get smaller and smaller and smaller cubes. So you need to remember that halite, the mineral halite, has a cubic structure to it. Now here's another very common mineral, calcite, very common out here in western Kansas in the limestones. Okay, calcite kind of looks like a distorted cube, as if you pushed one of the corners down and you create a different structure we call a rhomb, or a rhombic kind of crystal form to it. And again, the sizes of the atoms, The number of the atoms and the bonding types are what are going to control that shape. It's very simple. The ionic sizes and the bonding style. And here's a nice sample of a kind of somewhat clear rhombic calcite crystal. The nature of this structure, the rhombic, the cubic, the orientation of the atoms in the structure, as energy or light passes through them or bounces off of them, control some of the colors of what that mineral is going to look like. And the shapes of that. Here's another interesting kind of off-the-cuff kind of characteristic of the mineral calcite. It possesses something we call double refraction. On the top left is a very nice clear crystal, rhombic crystal of calcite, and underneath it on a piece of paper is written the word calcite. When you look down through the top, you see the ghosty pattern of it. You're seeing a double. Because the light coming up from the paper, as it's reflected off the paper, coming back to the crystal, the rays, the vibrational directions are converted at 90 degrees to one another. They break it up into what we call the O and E ray in mineralogy, and you see kind of a ghosty pattern from that. So not all minerals have this, but sometimes it's a characteristic that's useful to identify what it is. Like I said, color, cleavage, hardness, all these different types of things are useful in identifying what the minerals are in geology. All right, let's jump to another interesting feature of minerals called polymorphs. Poly meaning many, morphs meaning form. So polymorphs are minerals that have the same chemical composition, but they have a different form, a different structure. And I'll have you memorize just one example of this type of characteristic in the class. An example being a diamond and graphite. Diamonds and graphite. They're both made of the element carbon, but under different conditions, especially pressure, you can change the form of one thing to another and create two different kinds of mineral shapes, one very soft and one very hard of the same composition. Here's some actual photographs of the polymorph of carbon here. On this gray material, the shiny stuff is simply graphite, like in your pencil, different hardnesses of lead. So this particular mineral, graphite, is very soft because of how the carbon atoms are put together. They're put together in an alignment such that they kind of have a platy, soft bonding between layers. So when you rub your pencil across a piece of paper, the bonds are so weak they break. And they slide right off and you leave a gray mark on your piece of paper. Now if you could take that carbon, take that graphite, and put it under extremely high pressure and squeeze it and collapse those carbon atoms together in the tightest knit packing you could possibly do, you change its crystal form. Now the only place that happens is deep in the earth. And what you wind up with are diamonds. You may have seen old shows of Superman grabbing a chunk of coal and squeezing it and he gets a diamond. All right, well, we can do that in a laboratory. In fact, we made a lot of them during World War II, and we still do, industrial diamonds. General Electric and many other companies make synthetic diamonds in this fashion. So remember that diamonds and graphite are polymorphs, and they're made of carbon. All right. Now the crust of the earth consists mainly of a particular group of minerals. And this specific group of minerals are made up of a unique building block, a unique tinker toy, or kind of Lego in this case. And there's a long name for it I want you to remember. It's called a silica tetrahedron. Okay? Tetra meaning four. And so this three-dimensional shape has four sides. And it's represented here graphically several ways. One is that we've got four large oxygen atoms, four great big large ions, oxygen, and then one really small silicon atom that kind of fits in the middle. Now the best way I could kind of describe for you to make one of these visually is take some basketballs, take 3 basketballs and lay them on the table and push them together, the centers of which create a triangle. Now take your tennis ball and set it in the middle on top, and then take your last basketball and lay it on top of that. So here we've got the 3 on the bottom, our tennis ball in the middle, our silicon, and another great big oxygen basketball sitting on top. Well, the geometry of that is very specific. You can only put those sizes together in a specific fashion. Now, this particular structure, of course, in 3 dimensions is a tetrahedron. Because it has silica in the center, we call it a silica tetrahedron, because it has to do with a group of minerals we call the silicates. Okay? The silicates are the major rock-forming minerals in the crust of the Earth. If you went out and did a study of all the average minerals, the main minerals that make up the crust of the Earth, all the basalts and all the granites and different kinds of igneous and metamorphic and many of the certain kinds of sedimentary rocks, they're all made of minerals that are silicates. Because the 2 most dominant elements in the crust of the Earth are silicon and oxygen. So this is our little basic building block right there. Okay? Now what we have to do with this thing is to put it together in certain arrangements to create a bunch of silicate minerals. We'll keep it real simple and talk about the beginning point of this kind of mineral. All right? So let's take a look at the first kind of. Over here is my little pyramid. See these little kind of blue or gray pyramids? And you've got some of the points of the pyramid sticking up towards you. Now you're looking at the bottom of some of the pyramids. When you cluster those together, these silica tetrahedrons are not combined with each other, are they? These other black dots represent other elements, iron, magnesium mainly, okay, that bond with different corners of those 4 parts of the tetrahedron, join up with the other electrons in that outermost oxygen on this thing. So since these silica tetrahedrons right here that I'm pointing to right now, since they are alone and not combined with other tetrahedrons, we say that they are single tetrahedrons. I see there's a misspelled word there. Tetrahedrons, all right? Please make note of that spelling on there, okay? Single tetrahedrons. They're all alone. They're independent. A very common silicate mineral in the crust of the Earth that's part of basaltic type rocks, not completely basalt, is this common mineral right here, olivine. And olivine also has another nickname called peridot. It's one of those monthly gemstones, okay? Here are some raw, natural peridot olivine crystals, all right? And here's one that's been faceted and kind of sellable as a gem. So olivine are the beginning points of a particular type of mineral and silicates that we'll find out later are major parts of igneous rocks, in particular basalt rocks. So what if I could take these little building blocks, the tetrahedrons, and do something else with them? Make them more complicated. In other words, find a new way to put them together, like molecules you might want to do in a DNA strand in biology. And how can I put the pieces of the puzzle together to come up with something different? Kind of challenges you might have in some geometry classes. Well, on the left-hand side of the diagram, what I've done is to take 2 of those tetrahedrons and have them share one corner. So this tetrahedron and this one share the corner right here in the middle. This one shares that corner and on down the line. So when you do that, what do you get? You get a chain, a single chain that has a very specific geometry. Remember the definition of a mineral? A specific chemical composition. That's what's dictating this specific atomic structure. A very ordered atomic structure to it. And when you look at this, if you started drawing lines through the geometry and then measured angles between your lines, you could find out that there's a specific alignment of that geometry. There's specific angles between them. If I could take a hammer and hit that thing, if those lines are planes of weakness, what do I produce? Cleavage. Cleavage with a very specific angle to it. So everything's starting to tie together now in terms of that shape, that it all goes back to what? The sizes of the atoms and the bonding characteristics and the strength of those bonds. What type of bond is it? So I'm not going to expect you to remember a name of, say, pyroxene being a single chain. What I want you to get out of this is that there's different geometries and very specific geometries set up by putting those little building blocks together in different arrangements, creating thus different minerals. Let's take a look at this one, the second one. Instead of having 2 single chains, now I'm going to have this silica tetrahedron share what? 2 corners of it with others. And look what I get. I get a chain on the right, chain on the left, so it's a double chain of minerals. But lo and behold, what have I got? A great big hole in the middle. Well, what could I put in there? Another atom. I could throw a larger molecule, like an OH, hydroxyl molecule in there, or I could put a bigger potassium atom in there. Remember, they're all different sizes. So you got these pieces and stuff, and if they're around in this, at the point when the minerals are forming, you're going to get different shapes and orientations. Notice that the join between this one and this one, the angles become different again. So when I bust this one, it's going to have a different angle to its cleavage style. Now, if I had lots and lots of time and I wanted to continue joining a whole bunch of chains laterally all the way out to the side, I could end up with something like this. I could continue to draw these over and over and over and spread the whole wall full of them. And just have one huge layer, and I got a hole here and a hole there and there and there. I could throw all kinds of things in there, like those little games with marbles, okay, or pinball machines. It's just chemistry in this case, and geometry. But it creates a long, complex chemical formula, which is going to have a specific mineral name that we apply to it. Have a certain color, a certain characteristic to it. And of course, these are the building blocks for rocks. This particular style of silicate shape over here is called a sheet structure. And they'll all be flat. So if I could take another piece of paper and lay it down and draw this again, and another one, the bonding between this layer here and the one on top of it, the one on top of that, is going to be kind of weak. Kind of a polar kind of bonding between those. So what would happen is I could peel that apart in a sheet structure and do this. Now, on the sideways, laterally in that structure, they're kind of tough. But between the sheets, between the layers, I've got a real weak bonding, another kind of cleavage, all right? And I can peel them apart in sheet structures. So I could take a knife or my fingernail and split those apart. So each of the minerals, each of these silicates have different characteristics again. So keep remembering why that is. It has to do with the mineral sizes and the chemistry, the sizes of the atoms and the types that are bonded. Now let's take the last character now. We started out with single tetrahedra, then we made a single chain, a double chain, and a sheet. Now let's take and build a structure where all we have is nothing but those silica tetrahedrons bonded with other tetrahedrons. Okay? Nothing but that. If you do that, every corner that's joined with another tetrahedral corner is going to have the same strength. So the strength inside that crystal will be the same whether you go right, left, top, bottom, sideways. There's no weakness in this mineral, and it's all silicon and oxygen. One of the most common minerals in the crust of the earth is this silicate right up here, quartz. Okay, quartz. And since there are no planes of weakness in that structure, and you try to hit quartz with a hammer, it will not break and cleave along planes of weakness. Quartz does not have cleavage. It's a strong mineral in this case. What atom, by the way, went in the middle of this silica tetrahedron? Silicon. Well, there's another atom out there, aluminum, that has about the same size. Once in a while, I can take silicon out, and I can put aluminum in the spot where silicon was. Fits perfect. Same shape, same size, nothing changes. But one thing does change. The electron character of aluminum is different. It's different than silicon. And because of that, that silica tetrahedron now has a different electron kind of charge imbalance than the one with silicon. And because of it, I've got to bring something else in to satisfy it, maybe a little sodium, maybe a little potassium. All of a sudden, I've created a whole new mineral that does have cleavage because I had to bring these other weaker substitutes in, so to speak, kind of like in a basketball game. You got somebody that may be the same height, but not the same kind of energy, so to speak, and you may give something up because of it. Well, this new mineral that's a framework silicate, another very, very common mineral in the crust of the earth, is feldspar. Okay? So we're kind of looking at some of these basic buildups of this, and here's some shots of quartz, by the way. A nice white milky quartz on the left, this pink quartz on the right, and here's a quartz crystal that has these crystal prisms on the side of it. And there's a reason why there's a difference on these minerals, is that, remember, quartz doesn't have cleavage, but you say, well, these are nice flat surfaces here in the middle. Well, if I took a hammer and broke this thing in the middle, I would not get little crystals that look like this. I would shatter it and get all these curved surfaces on it, because quartz does not have cleavage. This mineral on the left and the one on the right grew impeded along other crystals. where they were confined and squeezed together and could not develop the internal atomic structure in an external form. This one did, like in an open void in a geode. So you can see where it's broken on the bottom. This part on the bottom doesn't look too much different than that right there. So I hope you remember all the different major characteristics now of what put these minerals together and why they are the way they are. The next thing I want to do is kind of just throw at you some other things about minerals that are out there, some that you may take advantage of in your everyday life and don't know it, and others that we're still trying to find something new, inventive to make with it. So if you're an entrepreneur and got some good ideas, who knows, you might patent something to be useful. So there's a long list of things I want to go through here. I want to have you write down the definition, the terms and the definitions, and we'll look at some pictures of what they are and a few applications. All right, so here's a mouthful for the first one. Piezoelectricity. Piezoelectricity is going to be a special property of a particular type of mineral. In this case, it's going to be quartz, that if you apply pressure to a quartz crystal, you can, in other words, squeeze it, you can cause an electrical current to move from one end of the crystal down to the bottom. All right, you can create electricity by squeezing quartz crystals. That property is called piezoelectricity, and somebody took advantage of that a long time ago, starting developing early radio. But today, some of you probably have something on you that has it with you right now and you don't know it. We'll come back to that in a bit. Pyroelectricity, if you heat certain minerals up, they will create electricity. Here's one you may have heard about, of course, fluorescence, minerals that fluoresce. If you apply an ultraviolet light to certain minerals, that ultraviolet light excites those outer electrons, makes them move positions, and those positions drop back and forth and they give off photons. Well, once you turn the UV light on, all of a sudden minerals will take on a totally different color. A very useful tool in some mines sometimes. You're going through in the dark mine, you use an ultraviolet light and scan, and you'll just see these minerals glow in the rock, and you get a real good feel for the percentage that's in there. Good way to identify certain things. Here's a weird one, very, very strange, that we haven't really figured out what to do with yet, but maybe somebody will invent something unique and get rich off of it. Triboluminescence. If you take certain minerals, and again quartz comes into play, take two large chunks of quartz and you rub them together and create a friction, or hit them with a hammer in a dark room, they'll give off light. That frictional rubbing generates kind of a heat. Electrons, get excited, move out, pop back down in their orbits, and then give off photons or light fashions. But it ends. It just stops once you stop the rubbing. So who knows what we could make out of that particular weird one. Here's one you simply apply heat. Heat them up, and they'll give off light. Thermoluminescence. And here's another strange characteristic you may or may not have heard about. Some things that we could make, usually some man-made crystals that can behave as solid crystals or can behave as a liquid under certain conditions if you do something to them. And again, you all probably have one of these on you right now in some way or in some device at home. We'll look at some liquid crystals in a little bit, another characteristic of it. Moving to something maybe more humorous or different, I want you to write this mineral name down. Or not mineral name, a product, excuse me, an infomercial here. Kaopectate. Have you ever heard of kaopectate or maybe used kaopectate? Sometimes it's a thickening agent. It will absorb waters, acidic stuff in your stomach, okay? If you've ever gone out and eat a whole bunch of jalapeno peppers or get something like that and you take kaopectate, or a thickener used in real old-fashioned milkshakes, something to make it stiff and thick, all right, is a clay. Now, kaopectate takes its name from a mineral called kaolinite. And kaolinite is a clay-like mineral that has the ability to, just like a sponge, suck up water and expand. And of course, it has certain chemical composition to it, and these minerals have some things that may or may not be beneficial. Sometimes there's magnesium, potassium. kind of like a little mineral, you know, a vitamin pill type thing you could take. And so if you have taken kaopectate, you've kind of gone through what we call a practice of geophagy. All right, geophagy. But in certain societies, people actually go out and dig up clays and eat them, or eat that dirt, clay-rich dirt. So the definition of geophagy is the practice of eating clays. Certain societies do this for they get their minerals that way, kind of their vitamin pills, if there's a deficiency because of the food. And they've learned to do that with time. If you've taken kaopectate, I guess, or some other kinds of goodies, you've done that. So those are some of the strange things. Let's look at what some of these things look like. Let's talk about the piezoelectric first. Again, if you apply pressure to a quartz crystal, up on the top left is kind of a schematic of a quartz crystal, a certain kind of thing. We can grow these things in laboratories. General Electric can make huge, 2-foot long, 6-inch, 10-inch diameter, perfectly clear silicon dioxide boules, quartz crystals in an oven. Have a nucleated thing and they pull it out of there and you get these really cool things. And if you take and slice these up into little thin wafers and then apply pressure to those wafers, you can create an electrical current. That's what piezoelectricity is. But what we do to use it in everyday life, we reverse the process. We reverse that process in watches. Ever heard of a quartz diode watch? Okay? In a quartz diode watch, inside that is a little wafer, little thin wafer of quartz. And attached to two ends of the quartz are two wires that are attached to the battery in your watch. And so we apply the electricity to the quartz wafer. What happens to it? It's going to wiggle. It's going to undergo pressure changes back and forth and back and forth and back and forth, about 300,000 times a second. Very uniform. That's a great clock, a timing piece, something that works very uniformly and very rapidly. So that's how we take advantage of it. Down at the bottom right is kind of a schematic of that process. Here's piezoelectricity on the left. We just reverse it to put it into a quartz watch. Quartz diodes. So here's a typical, one of those common watches, a G-Shock, out here by Casio. All right. So the way in which this timer functions is using that piezoelectricity concept. The number system that you see on here, though, has to do with liquid crystals. LCD, liquid crystal displays. All right, here's a liquid crystal display in a calculator. Some of the newer televisions coming out with liquid crystal displays in color, kind of competing with the gas ones, the plasma types. Well, what is it? How does this function? Well, you've got two slabs of glass, and sandwiched between that glass is this liquid crystal material. And then on the inside of the glass, attached to the glass, is a little pattern array of things that when you put electricity through that boundary between the two, all of a sudden the liquid turns to solid crystal and you get a little number popping up in a very specific geometric pattern. And the time changes. It's all controlled by your little computer chip inside your watch. It's amazing, nice little technology using things of crystal. So I'm not going to quiz you on what LCDs and what they are, but just for your own knowledge of what a liquid crystal display works, you got liquid crystal between two layers of glass, and then you have this transparent electrode pattern that's applied to the inner surface of that glass. Okay? And they're set up in different bar patterns, kind of geometric bar patterns. And then the circuitry that's applied through the computer chip in a sequence of pulses then controls what's going to happen to the arrangement of those liquids that become crystals attached to those bars. So you apply a certain voltage to specific segments and boom, the liquid becomes a solid, i.e. a crystal. That's where the phrase liquid crystal comes from. So it's kind of interesting what happens, and there's quite a contrast between the material inside the watch, and so they stand out quite strongly and you can really see them quite well. And you're looking at reflected light too, as opposed to transmitted light. So when you do that, you don't really need a lot of electricity in your battery. Otherwise they'd wear out pretty quickly. So it's a unique thing that somebody came up with, took an idea of a mineral property and has made a fortune off of it. So you just never know what comes next, what goofy things we can find in minerals. Here's our everyday blah, drab shelves full of rocks and minerals on the top. Go in a dark room and put ultraviolet light on it, and boom, all the fiery different wild colors come out. Now some minerals do this and some don't. Some minerals do it and some don't. We used to have a display at Sternberg Museum, and they may or may not bring it back. You used to go into a little curtain booth and you'd pull the switch or push a button and you could see all this happen. And petroleum, different kinds of crude oil, will have different colors to them. Different weights of oils, and the oil fields they came from will also fluoresce. So it's just another kind of technology of seeing things and seeing the capability. And some of them are pretty spectacular, like in these shots here. Triboluminescence, here they're hitting a particular material with a hammer here, and then they take an image of it, and it glows and gives off kind of a light from the pressure that's applied to it. I could do a demonstration here if I had to. You know, get the room really dark and take two big chunks of quartz and just rub them together, and you can do the same thing. You see that energy, triboluminescence. Thermoluminescence takes some everyday natural minerals. I think these might be some fluorites, and heat them up and they'll glow in the dark. Another useful toy. Now look at this. This is kind of going off in a different direction a little bit to end up our business on minerals. We started out with good-looking diamonds and all kinds of wild gems and stuff, but there are some natural crystals in nature that are so huge and so strange, they kind of take on that character. I found a website. It had to do with clothing, outdoor clothing. And it was a photographer who was kind of talking about this spot he found. All right? And what he did, he found a cave. He and some other people found a cave in Mexico. And underground, they got into this cave, and it got hotter and hotter and hotter as they got deeper in the earth, 120, 130, 140 degrees. And the humidity was 100%. They got into a void, a hole underground, where it's kind of like the steamy kind of spot where something was going on. They were near some hydrothermal activity, hot water activity. There was probably magma deeper down in the ground, and the groundwater is coming back up in this steamy vent and humid kind of climate, and precipitating out in this hole underground were these minerals, precipitating out of this moisture, out of this liquid in this hydrothermal kind of environment. And the crystals looked like something out of a movie from Journey to the Center of the Earth. Huge, 60-foot, 80-foot, 100-foot long individual crystals, feet thick, 3, 4, 5, 6, 7, 8 feet thick. Unbelievable sized crystals. You can't stay in the cave too long because your cameras will start to go and you start to get faint, and you've got to get out. I want you to write the name of the place down. If you ever get the itch sometime to find. They found a new one like this in France, but this is the one in Mexico. The Naica crystals. The Naica crystals in Mexico, in these huge, spectacular looking crystals. And again, this isn't fake or set up. This is a real spot. They're a form of gypsum, a calcium sulfate type mineral, very common mineral we find out here in Kansas. The special shape, this kind of rhombic, remember the term rhombic I used earlier? This kind of rhombic style of shape that you see in here, the type of gypsum that has that character is called selenite. So selenite is a name for a certain form, a crystal form of gypsum. But it's one wild place, kind of unique. So I wanted to kind of use that up to wrap up this concept of minerals and work our way into rocks now. So atoms are the building blocks for minerals, right? Minerals are the building blocks for rocks. So this next segment deals with rocks and some of the features and characteristics about rocks I want you to remember. So what is a rock? In a real super simple definition, it's a natural mixture of minerals. A natural mixture of minerals. And I want to bring back the rock cycle from the last lecture. Remember now in the cycle you can start anywhere you want, but I want to kind of start down here with these igneous rocks where deep in the earth magma is produced, liquid rock, and that liquid becomes less dense, or it is less dense, and so because of that it rises towards the surface. Some of that material that rises to the surface comes out on the surface as volcanoes. Some of it remains below the surface, intruded inside the earth. But eventually those rocks get exposed to the atmosphere. They're going to be hit by water and ice and wind, and so on. They're going to be physically and chemically broken down, and all those nice crystalline natures of igneous rocks are busted up. Smaller and smaller pieces are produced, and glaciers transport them, and wind transport them, and all these little fragments are called sediments. Well, these sediments then are being washed off the continents towards the oceans and lakes by what? Rivers and streams mainly. Brought there in big masses at delta systems and deposited, and then they get buried. They get buried deeper and deeper and deeper, and then these sediments become hardened and cemented together and become a new second kind of rock called sedimentary rocks. Well, I could take that rock and bring it up and re-erode it too. But if they keep on going down deeper and deeper and deeper, heat and pressure build up, those two parameters we'll see change the sedimentary rock and reconvert it to a new and third and last kind of rock called metamorphic rocks. So we're going to look at each of these. Look at examples of pictures of each of these in the next several minutes here, or the next half hour roughly. For general purposes, I'd like you to at least be aware that igneous and metamorphic rocks, these two rocks on the bottom of the chart, because of their nature and how they form, are the strongest types of rocks. They're much stronger in their ability to resist erosion and breakdown, and thus geohazard type problems, than sedimentary. So on the average, sedimentary rocks are the weakest. And so if you're an engineer, you want to know which of all the rocks are strong, which are weak, and under what different conditions. And we're going to look at some of that and how they analyze that. And one of the things we'll do as structural geologists or engineers is we like to torture rocks. We'll go out to a mine, a road cut, a quarry, under a house and whatever, and we will core into the rock and bring a sample back. We bring the cylindrical core of rock back to our laboratory, cut it up and prepare it to put it inside of this, an apparatus like this. Over here is kind of a schematic blow-up of this device here called a Dunneth apparatus, a rock squeezing kind of device. You can see the big wheels here to crank up pressure and torture it, so to speak, and then break it and see how strong it is. Watch what happens to it. And the little core, the little sample, is this little piece that's inside this large anvil crushing device inside there, and you squeeze it together. And you can change the pressure, the temperature, you can change chemicals, fluids, whatever you want. You can play any kind of variable game you want. Say, what do I do to break it? So I take a marble, I take a granite, I take a basalt, I take all these different rocks, I take them into a lab, and I bust them. And I crank it up and say, how is it doing now? How is it responding? Is it starting to bend? Is it starting to squeeze? Is the energy being stored? What's happening to that rock? Because that's exactly what's going to happen in nature. And if we're dealing with rocks and highways and mines and quarries, and they can have problems for us, okay, then we know what to do about it. We can try to find a way to fix it. And later on this semester, we'll get into the chapter on that. We'll go into it in much more detail. So we can squeeze that rock. Here's a shot of a real granite that they broke, and it split in certain fashions on our device. And so that's what we want to see. How do they break? Do they bulge? Do they bend? Do they just brittlely crack? The weakest links, so to speak. All right? What's going to happen to that rock? Kind of fun. So in looking at mine safety, you always have people going into the mines to check a number of things. From the chemistry of the air in that mine to the roof, to the floor, to the walls. Are they cracked? Is the roof sagging? What's going on? How many cracks do I have? Because if something happens and the mine roof collapses or the walls explode, you're going to kill somebody. And it happens all the time. So once we analyze what's going on with those specific rocks and know how they behave, what their strengths are, we can attempt to fix them. Now here's an example of one attempt. Here they've got some wire mesh over the top and the walls. This is a very, very deep mine. This is a gold mine, miles below the surface. It's very hot in this mine, so they have to try to do what they can to vent it and cool it off. They need electricity down there for the lighting. But more importantly for the miners, that rocks that were deep in the earth are under extreme pressure. It's a special parameter I won't give you the name for, but because they're under pressure, and we've dug a hole through here, we've released a little of the pressure. So the rock's sitting there with stored energy that's been there for millions of years. But all of a sudden, on one side of that rock, we don't have anything pushing against it anymore. and all of a sudden that pent-up energy just explodes. And a rock fragment, slab, sliver, whatever, will come blowing out of there like an explosion from a gun. And every year there's usually 20 or 30 miners that are killed because of this property, called Poisson's ratio in physics. It has to do with stored energy. And these things explode. So what they do is they will take and protect that particular mine area with some mesh. If that's not good enough, let's go in and shore it up with even some more stuff and staple other big steel things up there and put rock bolts into the ceiling, whatever it takes. So mining safety has improved and come a long way in the last 100 years because we're still underground and we're still doing it. It's still part of geohazards. So knowing the strength of rock is really important. I'm going to look at the three general categories of rock types. Okay? Igneous rocks, which I'll kind of define in a little more detail and show you some pictures of in a bit. These are strong rocks usually. Metamorphic rocks, usually strong, like I showed in that rock cycle. And sedimentary are usually the weaker types of rocks. And we're going to look at, again, at all three of these examples in a little more detail. So what is it that really is part of the strength? You could have an igneous rock that could be weaker than a sedimentary rock if that igneous rock were very weathered, very shattered, very old and broken down. Okay? So on the average, they're strong, and weak in the list, but that strength depends upon fractures that are already in the rocks, how much it was weathered, what kind of gluing or cementing agents it has, and a number of other variables that come into play. So strength is important to geohazards. Highways, mines, quarries, dams, and the list goes on because things can happen that can create a problem to humans. I want to use this kind of schematic three-dimensional block diagram to kind of point out again where some of these rocks are forming. Now, igneous rocks form from the crystallization of liquid rock, magma. All magmas are generated somewhere in the upper mantle. In this diagram, here we have some magma generated at a mid-ocean rift, okay, where the temperatures are high enough and the pressures are low enough that part of this upper mantle melts and squeezes up through that fracture and creates kind of a mountain chain at the bottom of the ocean. Magma oozes out and squeezes out on the bottom of the sea. So that's one place where we can get igneous rocks forming. Here's a place, like the example could be Hawaii, where the Pacific plate is moving across a fixed hotspot in the upper mantle. Again, the same things happens, and right in there, magma is generated, and it squirts up through that. And as the plate moves across, this is the old island, and this is a new active one. So a whole series of chains of volcanic islands could link in a condition like that. But again, it's still the upper mantle where it happens. And lastly, say here where a plate goes back into the mantle, subducts down, and we'll look at that in the next chapter in more detail. We can partially melt some of this, and some of that magma comes up, creates a mountain chain above the ocean, like the Andes Mountains or the Cascade Mountains out west. Or some of those magmas stay below the surface and cool off down here. We can have intrusive rocks or volcanic extrusive rocks, different kinds. Now, I'm not going to spend a lot of time on all the detail of volcanics and intrusive and plutonic rocks here, more specifically to gloss over it in terms of what it is. These rocks that are above sea level are being attacked by air, water, ice, wind, okay? So what's happening in the rock cycle here? They're being broken down and sediments are being produced. Where do those sediments go? They're washed back down to the ocean. So along the edge of our continents, we have shorelines, deltas, beaches. It all gets dumped back in there. So we build up sediments and sedimentary rocks on the margins. That's where most of our sedimentary rocks are created. If we look closely at the sedimentary environment, we could get even into more detail. There's a whole class you could teach on simply sedimentary environments. Did this sandstone form in a beach? Did it form in a dune like in the Sahara? Did it form in a lake? Did it form in the deep ocean? So all those products can create different kinds of styles of sedimentary rocks. And again, we're not going to go into detail of this diagram in here, but you have to be aware there's lots of different ways in which you can produce igneous rocks, metamorphic rocks, and sedimentary rocks. Let's go back to this diagram here with metamorphic rocks. As you bring this slab down, okay, you're hitting two plates head on. This plate here is moving to the left. This one's going to the right and going down. They're hitting head on. It's a big demolition derby. They're colliding. That's a lot of pressure. Pressure is one way of changing rocks to make them a metamorphic rock. You're dragging it down into the earth. What's that? That's heat. It gets hotter down here. These magmas come up. That's heat. So those two parameters, heat and pressure, create a whole new group of rocks down here underneath in that spot called metamorphic rocks. And then once in a while, boom, a little igneous intrudes through it and cuts to the surface or remains in the subsurface, and those are igneous rocks. So it's that cycle. It keeps going round and round and round. Here's a picture of an igneous rock. Okay? Igneous rocks have a very distinct look to them. They're very crystalline. They have a distinct interlocking crystalline texture to them. And here we have two kinds of igneous rocks in this particular outcrop. Okay? But you see that interlocking crystalline nature of those individual minerals in here. The white ones are probably feldspar and quartz. These dark ones are probably the certain kinds of micas or the single chain and double chain silicates we looked at. Here the crystals are just tinier between the two. But the key thing to remember for igneous rocks is how they form. They form from what? The cooling of magma. Magma being liquid rock. This one shows that interlocking nature even better. Okay, that nice crystalline texture. They're very, very hard. So you can see great big individual crystals here in the pink and black and gray, whereas in the middle you can't see individual crystals. They're too tiny for the naked eye. And the reason why some crystals get big and some get very, very tiny has to do with how fast did the magma cool. Okay? How fast did it cool? Well, if the magma stays below the surface of the earth, it's going to be kind of protected by the blanket of the surface of the earth, so it's going to cool off real slow. A long, long time, sometimes millions of years. When they cool off slow, big crystals form. So this shot right here with this pink or red and black and gray with the big crystals, that cooled slowly. And it stayed underground. It was intrusive. I don't know if you can pick up on the edge of that on the screen here, but that's intrusive, I-N. Okay? Meaning it stayed inside the earth. Intrusive. Now later on, some other kind of magma squirted up through a fracture closer to the surface of the earth, or when this was at the surface, and did what? Cooled off very quickly. So when you get tiny crystals, small crystals, that's faster cooling, more rapid cooling. Nevertheless, it's still this mass of interlocking crystals, and they're still very, very strong because of that interlocking characteristic. Here's a good example of an intrusive rock, granite. You have to remember the word granite. Granite is a good intrusive rock. Another fancy name geologists use for intrusive magmas are plutonic. Plutonic. I think for all general purposes, for the quizzes or the test, I'm using the terms intrusive. Granite is an intrusive rock, very slow cooling. What's an example of a faster cooling one? Basalt. So basalt is a type of magma with a certain kind of liquid nature to it. It's much runnier, much soupier, makes it to the surface of the earth, becomes extrusive. Volcanic, comes outside the earth. Once it's outside the earth, of course, it's going to be exposed to the air. It's going to cool a lot faster. It's not insulated, so it cools fast, little tiny crystals. If I could take this liquid magma and cool it instantly, just freeze it really fast, the atoms have no time to bond in some orderly arrangement. There are no crystals. So, instant cooling, that means instant. Sometimes just a second or two. Creates a glassy texture. Glassy means no minerals. And this rock right here is a real good example of a very common kind of glassy textured extrusive rock. It's called obsidian, also known as volcanic glass. And because it fractures in this fashion, this conchoidal fracture, doesn't have individual minerals or weaknesses in it, it's easy to chip and create kind of arrowheads or points out of it in the past. So just remember that obsidian is an extrusive material that cooled instantly. So it's a fairly weak rock. It's kind of brittle. And we've got this rock here. It's got two kinds of crystal sizes. These great big white things, large crystals, surrounded by this matrix of fine-grained stuff you can't even see. So what happens here is that under the ground, this thing was cooling off, and these big white crystals started to form, and the rest of the stuff was still liquid. But something caused the mass of that whole magma below the chamber, those big crystals growing in it, to be squeezed and squirted to the surface, on the surface, such that the rest of that liquid cooled rapidly and created real tiny crystals, sometimes even glass. So what you have are what? Two cooling stages. The very special case of rock you need to remember that does this is called a porphyry. Okay, it's a porphyry. And so what you have are two crystal sizes because of two cooling stages. So this sample was both, intrusive for a while, and then boom, got squeezed out and became extrusive at the end. Now let's jump to our second major category of rocks. Remember I showed you that kind of diagram of all the different depositional environments, the beaches and the deep sea and the mountains and the dunes and so on. And here we have like beach-type deposits being formed. That's where the sedimentary rocks form. A lot of sedimentary rocks preserve features in them that help us figure out where they formed, like this one. Okay? Those sediments become lithified, those sand grains, those quartz grains, those feldspar crystals, whatever they are, get buried deeper and deeper and cemented together and lithified into a new hardened rock. But while they're going through that, wave action, currents of the rivers, wind, organisms burrowing into them, organisms dying and having their fossils, the shells and skeletons preserved, they get stuck in those sedimentary rocks, and so they're clues to where. So here we have this rock in Dinosaur National Monument with all these little ripple marks on the surface of it. These are ancient beach ripple marks along a coastline. So we can unravel not only that it's the fact that it's a sedimentary rock, it's a sandstone type of sedimentary rock that has evidence of where it formed. Dinosaur National Monument is one spectacular place to go visit if you ever have the chance. Here's 3 of our students from Geology Field Camp just this last summer, Field Camp 2003, sitting out here. They have a 4-day project. We camp out along the river and they have to go hike all through these areas with air photos and identify rocks and make maps. And so they pull those clues out of the rocks. Everything they learned for 4 years they apply in this particular field project. They have to do it, kind of a graduating, seniors have to do it to graduate. So what is it about sedimentary rocks, some of the things that they have that are unique? Well, they have fragments of material. They have what we call broken off pieces or clast. The word clastic comes from the word clast, which means broken off, weathered, fragmented. So this picture here shows us kind of a coarse-grained sandstone, which is one kind of sedimentary rock, and you can see individual rounded pebbles. They got rounded by wave action or moving down the streams and bounced along. Excuse me. If those clasts get bigger, we can define another type called conglomerate. A very coarse-grained rock. So a specific depositional environment with this. Excuse me. What about the types, though, that could be of a different composition? Out here in western Kansas, we have lots and lots of limestones. Limestones are formed of minerals that are chemically and biochemically precipitated out of seawater. And you think of some things that live along coastlines that precipitate minerals like calcite out of water. If you went down to the Florida Keys, have all the reef structures. You have organisms that live out in that water that are precipitating calcium carbonate out. You, as humans, precipitate stuff out. Your bone structure, your teeth structure, they're chemically precipitated by you as an organism. It's your endoskeleton. It's what's inside of you. Some things are on the outside, like clams and shrimp. Well, when those organisms die, their shells and material, their skeletons, get crushed up and become part of that sediment to become part of the rock record, part of a sedimentary rock. So limestones are extremely important for a number of reasons in time, and we'll see later on about a locking of carbon in a carbon cycle in here. But biochemical precipitates create most of the limestones that we see in the world. What's so unique about limestones is all the fossils that they contain. And sometimes they're practically all fossils. On Fort Hays State's campus, nearly every building has practically nothing but limestone in it. Limestone from western Kansas and limestone from eastern Kansas. And these limestones, like this is Albertson Hall, the south side of Albertson Hall. This is the fence post limestone, the famous unit out here, kind of a marker bed. And you look at this blah yellow part, and you just say, I don't see any fossils there. Oh, over here I see a great big oyster type fossil piece, and here's a great big fossil. If you can find this, this happens to be a fish scale, a giant fish, 15, 16-foot fish called Xiphactinus. And when it died, the scales got caught up in the muds of a shallow Cretaceous sea. There's some really cool fossils on the buildings around here. But this microscopic part, you can't see fossils, but under a scanning electron microscope, you'd see billions of little tiny pieces of microscopic single-celled organisms, fossils, foraminifera, coccoliths. These rocks are very soft, okay, so they're kind of weak, but again, they're very useful to identifying the depositional environment that they formed in. So we're surrounded by all this stuff, whether it's igneous or sedimentary, and here's our third and last category. If you look at metamorphic rocks, they've been squeezed and heated and changed. They're altered by heat and pressure, and they get all new textures and all hardened, and it all takes place in the solid state. And you often get a lot of nice banded, folded character like you see in this picture here. So metamorphic. Meta means change. Morph means form. You're changing the form. You're changing the texture by applying heat and pressure. So let's take a look at it. The metamorphic rocks are rocks that are altered in the solid state. And I put solid state in quotes because at the atomic scale, things can dissolve and migrate. But we're not melting the rock. The key thing is that we're not melting it. We're not heating it up. If we do that, what category are we in? We're back to what? Igneous rocks again. So by doing this, by jacking up pressure and temperature, you're going to create new textures, meaning new grain shapes, and sometimes new minerals because minerals become stable at higher pressures and temperatures. You can create new rock types. Now we can have just temperature alone, or just pressure alone, or we can have them working both together. Most metamorphic rocks that you see are a product of temperature and pressure working together deep in the earth. And they're brought to the surface later on by erosion and uplift of the crust. So let's take a look at some of these kind of rocks. I'm sorry, I had one more parameter. I forgot fluids. Okay, depends on what kind of fluids they are. Water vapor. That will change the pH and EH of that condition and drive your chemistry one way or the other. So the two most dominant ones to remember, though, are going to be temperature and pressure. So let's take a sedimentary rock that was made of mud. All the muds out in our continental shelf or in the bottom of a lake. If you bury them very, very deep, those muds turn to shale, a sedimentary rock. If you flatten and squeeze under high pressure and temperature shale, you end up with a metamorphic rock called slate, like the blackboard slates. They cleave really easy and split along the clays of those muds, those parallel layers. So shales are soft, slates are harder, all right? So slate's a much stronger rock in this case. So the parent rock, where it came from, shale's the parent rock, slate is the product. That's the metamorphic rock. Well, what about marbles? If you metamorphose limestones, you get all these wild, unique marbles. There's a whole range of them. Pictures here, just kind of pudding stone, one on the bottom, more marbly white. A lot of decorative kinds of stones in different buildings around your cities and towns. Right on campus we have a lot of these in place you can go look at over in Sheridan Coliseum in the lobby. Some very spectacular, beautiful looking marbles over there. But the parent rock is a limestone. And you apply heat and pressure to that and metamorphose it, you get marble, much harder rock. If you take a sandstone, a nice quartz sandstone, and you metamorphose that, this would be our parent rock, and I squeeze it together, I get quartzite. We call it quartzite because most sandstones are made of what mineral? Quartz. So sandstone on the right and quartzite on the left in the picture. Quartzite is a very, very hard rock. Very good, strong type of structure. Sometimes they take on this banded kind of character we can see here, a nice banded gneiss. So the banded nature, again, these squeezed, interlocking, new mineral sets, new textures are very diagnostic of metamorphic rocks. There are some other strange things that come out with metamorphic rocks as well. I know if you head out into the Colorado Rockies and go along the Arkansas River Gorge, west of Canyon City, Colorado, there's some spectacular, really old, banded, layered rocks that have kind of a linked sausage-shaped character to them, like they're squeezed in places and pinched along the way, like right here in the top inset picture. The word boudin means sausage shape or sausage-like. It's a French word. Boudinage is the process of boudin. Okay, next time you're at Oktoberfest, instead of getting a sausage, you can ask for a boudin. See what happens. All right, but this sausage-shaped feature you might want to remember is the word boudin. I might throw that at you in the quiz in some way or on the exam, just to kind of throw an extra word that I don't believe is in your textbook. Something different. Carrara, Italy, small little town up in the mountains, is a quarry town. Okay? Up in the mountains you see this huge light-colored rock called the Carrara marble. It's a metamorphosed limestone. It's one of the world's best limestones, the Carrara marble. And if you've had some art classes, you probably know that there was a gentleman named Michelangelo who took that marble and created some of the most beautiful statues in the world. The Carrara marble had, it has this perfect crystalline nature to it, fine-grained and useful, not a lot of false parts in it. And so they could, create very smooth, usable things that wouldn't break. Here in town we have Pete Felton, who takes local limestones from here or limestones from Indiana and chisels them and carves them into different statues, but he can't quite get that same smooth textural nature as you can with this marble, because one's a limestone and this is a marble, but very spectacular ones. Well, the Carrara marble quarry was getting quarried out. It was getting worn out, because as they got to the edges of that deposit, it got crummy. It was not as good to work with as an artisan. And so all of a sudden there was a quarry that was used in our country. This is a photograph of a quarry out in Marble, Colorado, of all things. That's the name of the town, where they quarried out a marble they named the Yule Quarry, kind of like the Christmas tree, the Yule log, the Yule marble. And it too had a really good character to it, and this kind of competed with the Carrara marble for a long time. But as they got deeper and deeper and deeper into the mountain out here, they had to shut it down because water was infiltrating into that quarry. At Carrara, they were working up high, working down. Here they're working on the side of the mountain going down, and they had too much water going into the quarry. So they shut it down. But a lot of the Yule marble was used in a variety of buildings around our country, particularly in Washington, D.C. The Tomb of the Unknown Soldier in Washington, D.C., and others are made of this Yule marble. So for 35, 40 years, that quarry sat still. But when the Carrara marble quality went down and the engineering capability to pump the water out of the mine and hire on some quarrymen, some master quarrymen from Italy, from Carrara, Italy, they came over in the early 1900s, they reopened the mine in marble, and the city grew, and and the tourists are coming in, the artisans are going, they're getting samples, and you can go to Marble and buy some unique statues and work with this stuff. So anyway, that's kind of some of the things on the side. That'll be it for today. Yep, it's all over, Rock. So anyway, we'll see you next session, and have a good week.